Okay, so we did an example yesterday where we took some function that we defined and we added up the area under the curve by the method of finite sums, right? Which all that means is by adding up rectangles, 5 rectangles in this case, right? And we did both a left and a right, and we got values of, I can't remember, we put it in a calculator, but you guys can all do that, right? That's not really a big deal. Okay, you're gonna get some practice with that. Not a huge issue, okay? But what we wanna do today is we wanna take this a little bit further, right? And what we ending up with yesterday is we said, okay, we could be tricky with this. If we wanted to, for example, add up the area under the curve f of x equals x squared on the interval from 0 to 2, we could let the number of rectangles approach infinity, and then the upper sum and the lower sums would converge on the exact answer, right? And we looked at, real quick, for those of you who didn't get a chance to see this yesterday, there was a pretty cool little site I went to.
Wait, you're allowed to go to YouTube?
I can go to YouTube. Yeah. They trust me.
Yeah.
Just not you yahoos. Oh, why did it do that?
What?
Yeah, it does.
It does.
It does exist,
I
yes.
forgot about it. Yeah.
All right, so we got calculus, applets. There we go.
Go straight to me.
So for example, if we were to take the area under the curve y equals x squared, how about, from 0 to 2, what we looked at yesterday, if we're looking at, for example, the lower sum, if we're letting the number of rectangles be 1, that's a pretty crappy estimate. We get either 0 or 8, depending on if we want the upper sum or the lower sum. As the number of rectangles goes up, though, you see that the upper and lower sums start to get closer, right? Start to get closer. And if we get out to 100, well, then it starts to look a lot better, right? We're starting to converge on a better answer. Turns out the actual answer is 2.67, 2 2/3, right? And so we applied this strategy yesterday to the same problem, right? Where we took this function, so f of x was x squared, our interval was from 0 to 2, so a was 2, and we're going to let the number of intervals n be n, and we're going to take the limit as n approaches infinity, right? And so delta x would then be the width of the interval divided by n, the number of rectangles, right? And so we come up with the expression, we always start with, if we want to be as general as possible, we'd start with the sum of rectangles defined at either the left or right edge, but being as we're going to let the number go to infinity, we're going to get an exact answer anyway, right? And so let's use the more convenient of the two, which is a right sum. So we don't have to put that I minus 1 in there, right? Does that make sense? Okay. And a is 0, delta x is 2 over n, so a plus I delta x just becomes 2I over n times delta x, right? And our function is f of x squared, right? So then we'd end up getting the quantity 2I over n squared times delta x is 2 over n. But what we talked about yesterday a little bit is because the 2 over n doesn't have an I in it, right? When we talked about this even maybe the day before that, we can pull that out of the sigma, right? Because the sigma is really only acting on the index variable I. So you can think about I as being sort of the variable of the sigma, right? We're gonna calculate what the sum is gonna be first, and then when we're done, we're gonna take the limit as n approaches infinity, right? So I can't pull anything out in front of the limit that has an n in it, because the limit is acting on the n's. Does that make sense? I'm kind of summarizing this. You were gone yesterday, Jonathan, and you guys are both gone, so it's kind of for you guys. I'm just summarizing this a little bit.
And those two.
You can go, oh, you were gone too. That's right, yeah, you were gone too. So most people in here were gone. So you guys are just getting the quick summary. You can go back and watch the video to get more detail if you want to, right? So what does this give us? Well, there were some summation formulas that I have chosen not to spend an inordinate amount of time covering this stuff, honestly, because I really am not. You'll see this again in college when you take calculus, and probably it's going to be more of a theoretical math class, and you're going to have more of your day devoted to calculus, and so you'll cover more material per day, and you'll probably see this at maybe a little different level. In the past, I've gone through this stuff, but I don't really care if you're good at this, good at calculating finite sums, because you're almost never going to do that, but you're going to do a lot of calculus. So I've chosen to kind of breeze through this a little bit and not spend the time, as interesting as it is. It's kind of a fun game to let you guys try to come up with these summation formulas, which you could do. It's kind of a math induction process, but here they are. These are the summation formulas. The sum of, for example, the sum of I from 1 to n. So the sum of 1 plus 2 plus 3 plus 4 all the way up to n. It's just equal to that. It's kind of cool. It equals n times the quantity n plus 1 over 2 every time. The sum of I squared from 1 to n is equal to this expression, right? Sum of I cubed is equal to that expression. So that's useful to us here because we can, in our evolution of this problem, when we square this out, we can pull the 4 over n out front of the sigma, and we're left with just the sum of I squared, which is this, right? So if I write that in terms of the finite sum, then what I end up with is inside of the limit, I've got this big expression involving n's. If we just simplify this, we get, if I expand that out and distribute, I just get this. I get 8 over n cubed times that stuff. If I distribute the 8 over n cubed, I get a sum of those three terms. What's interesting is, though, in the limit that n goes to infinity, all the terms that have n's on the bottom are going to go to 0. And so we're left with 3 of the terms are extinguished, and I'm left with just that first term, which is what? 8/3 is 2 2/3, right? That's what we found the actual area to be, right? Okay, so that's our process of finding a limit, or finding an area under the curve exactly by the limit approach, which would be the limit of the finite sum as n approaches infinity. And so I'm going to expect you to be able to do that on the assignment. You got to be able to do that a couple problems, right? But that's not going to be our focus, right? So today, let's take this one step further, right? So we can say now instead, because that is going to work in all cases, let's take this process and replace it with something called a Riemann sum. So a Riemann sum is going to say, if we want to add up the area under a curve, well, let's just make this as simple as possible. Instead of, we're going to move from this. What we did yesterday is the limit as n approaches infinity of the sum of f of x sub I delta x as I goes from 1 to n. We're going to write that instead just slightly differently. We're going to write it, the Riemann sum, as the limit of the sum of f of c sub I. C for convenient in my mind. That's a good way to remember it. What's the most convenient place on the ith interval? X sub I, right? But in terms of a Riemann sum, we'd always call it c sub I because it could be any place on the interval. If we go back and, if I were to pull up and go back and look at our, remember that graph or that picture we drew the other day with the individual rectangles, right? The most convenient place was, if I just quickly throw that up here, so there's our function, there's the ith interval, right? Well, the most convenient place is x sub I because that's a plus I delta x. This was x sub I minus 1, which is a plus the quantity I minus 1 delta x, which complicates things a little bit. And in between it can be more complicated, right? So we'll always just choose the right edge of the interval, but we have the freedom to choose anywhere, because in the limit that the width of this interval goes to 0, it doesn't matter where I choose, right? It's going to fit the curve perfectly. You get the idea? Okay?
For the left sum back on the graph that you just drew.
The left, say it again.
The left sum, the x of I minus 1, is it always going to be minus 1?
Yes, it is, right, because remember, these are discrete steps, right? We're taking steps of width delta x, okay? So yes, it would. It'd always be one step backwards from the ith step. The right edge of the I minus 1 step is the left edge of the ith step, okay? So this is then going to be as I goes from 1 to infinity. Actually, hang on, they write this in terms of the norm. I just want to make sure I write this the same way our book does, because you're going to be looking in our book, because I'm going to give you some assignments from the book on this. So the book's going to write this as the norm goes to, where's my Riemann sum? Right here. Okay. Yeah. Okay, that's fine. So 1 to n. I don't know why I put infinity there. That's kind of dumb. 1 to n. You can't do that, right? 1 to n of f of c sub I times delta x sub I. That doesn't seem like much, but it's significant. For us, it's not going to change anything. But what that's telling us is that delta x does not have to be uniformly sliced. Okay? In some cases, like if you were doing this with a square root function, for example, it wouldn't be convenient to slice it. You wouldn't want to slice it uniformly. You'd actually slice it where it would change as a function of x. It would be like it'd go as x squared, for example, for reasons I don't want to go into. Because once again, I don't care if you're experts on finite sums. But this gives us the possibility of having those thicknesses be non-uniform, right? So where it's indexed. So delta x sub 4 could be different than delta x sub 3, for example. Okay. In practice, it doesn't change anything, because we always have the freedom, if we want to make them uniform. It's fine. Okay, but then the part out front then, instead of letting n go to infinity, what we're going to do is we're going to let the norm go to 0. What that means is the norm is how we define the widest subinterval, right? So let's just say that delta x sub 4 is wider than delta x sub 3. As long as delta x sub 4 goes to 0, then doesn't delta x sub 3 have to go to 0 also if delta x sub 4 is bigger, right? So if the widest subinterval is going to 0, it's going to take everything else with it, right? So this is technically the way we write a Riemann sum. And it's in your book. It's in the textbook. That's no big deal. But typically what we would say is, okay, this is the Riemann sum, but for convenience sake, let's just let delta x equal b minus a over n, which means if that's true, if delta x equals b minus a over n, if they're all uniform, then we could just take the limit as n goes to infinity, right? That's going to accomplish this anyway, right? Because that's going to make, they're all the same width, and if n goes to infinity, that's going to make delta x go to 0, right? So this is almost like the fine print at the bottom of a legal document. It's like we're saying, all our options are open here, right? But we're going to do this anyway, because it's easier, right? Does that make sense? Okay. All right, so next stuff. So let's look at a couple things here. I want to do, let me just look here at 4.2. I think we got everything we need to out of that. Yes, we did. Okay. I gotta grab my notes for this one, because there's some algebra that I don't remember off the top of my head. I set this up, but it's super cool. I want you to see it. It's not in our book. Here it is. Oh, it's so cool. So cool. Okay, let's try this. So let's take the problem f of x equals, here it is. Yes. Good. F of x equals x. Okay. I don't think we're gonna finish this today, but we're just gonna pick this up. This will be like a couple day process, but this is really a good one. This is what gets us analytically to a process that's a lot easier. Okay, so first thing I want to reinforce here is, if we're adding up the area under this curve, do we even need calculus? Do we? No, that's a straight line curve, isn't it? Right, so if I were to graph this thing, it's just gonna look like, it's just gonna look like this, right? That's the function f of x equals x, y equals x, right? And if we're gonna add that up from A up to B, well, we're just adding up that area, right? That's no big deal. What's that area gonna be? Yeah, so if f of x equals x, that's A, right, and that's B. Everybody agree? Okay, so add it up. What's it gonna be? You guys can do this. I could either think, if there's two ways I could do this. I could make it a trapezoid, I guess, right? Which would be fine. Or I could make it a sum of a triangle and a rectangle, right? Either way, let's make it a trapezoid. What's the formula for the area of a trapezoid? Yeah, but okay, but here's the thing though. Like I always tell you, don't remember the formula, because I don't. Honestly, I probably could coax it out if I really thought about it, but I never try to remember. I don't remember formulas. I just remember how you get the formula, right? Getting the area of a trapezoid is easy. If you just take a trapezoid, let's call that B1 and that B2 and that's H, right? Well, how do you resize this to make it something convenient? What would you do? Yeah, we'll make it rectangular, won't we, right? We'll just take, there's the midpoint of that section, right? We'll just flip that around so it goes there, right? So then what's gonna be the length of both of those sides then? B1. Well, let's look at the total length, right? Because really this is just a sum of that distance and that distance, isn't it? Because I'm just going to subtract a little bit of the blue here. Everybody see that? So this part right here is just going to end up going right there, isn't it? So would you agree that the sum of that distance and that distance stays the same either way, doesn't it? Right? So then it must just be the average of those two, isn't it? Because would you agree that that side is going to be congruent to that side? Right? So then it's just B1 plus B2 divided by 2, isn't it? Times H. Got it, right? There's your formula. See what I'm saying? So you can always get that now. I mean, you just think about that picture in your head and you got it, right? So there's the area we're looking for, right? Only instead of B1 and B2, this one's turned sideways. B1 is A and B2 is B, right? And what's the width? Well, B minus A, right? So what do we get then? Okay, so we get area is going to be A plus B over 2, right? Times B minus A, right? Well, if I multiply straight across, this is the same thing as b plus a times b minus a, isn't it? Right? So don't I just get b squared minus a squared over 2? Everybody agree? Okay. I'm multiplying conjugates on the top, so I get a difference of squares. Everybody good with this? Okay. So now let's see if we can find this a different way. Let's find this using our limit approach that we just used and see if we can see a pattern coming out of this. Okay. So if we add this, let's just draw the ith rectangle. So there it is. Let's make it a convenient one. Let's make it the right rectangle, right? And so the area is just going to be, by a Riemann sum, is just going to be the limit as n approaches infinity. We'll cut this thing uniformly, right? So we'll define delta x to be b minus a over n, right? Okay. So it's the limit of the sum of f of a plus I delta x, right? Times delta x as I goes from 1 to n, right? Okay, what's our function here? Well, it's just x, isn't it? F of x equals x. So f of han just equals han. And so this becomes the limit of the sum of a plus I times delta x. But what's delta x? B minus a over n, right? Times delta x, right? As I goes from 1 to n. So what could we do to clean this up? I could, if I want to, I could take this guy and pull it out in front of the sigma, because there's no i's in it. Okay? And that's going to give me times the sum of all this. Okay, so now I've got the sum of a plus b minus a over n times I as I goes from 1 to n. Well, that's just two separate sums, isn't it? Right? I could write this up as the sum of a plus the sum of b minus a over n times I. Okay? And here's where those formulas, those summation formulas I gave you yesterday kick in. This one you don't even need a formula for. If I'm going to add up a plus a n times, what's that equal? A times n, right? Okay, so we end up with so this one is just going to become a times n, okay, plus b minus a over n times the sum of I. Well, the sum of I, remember, is just n times the quantity n plus 1 over 2, right? Okay. Oops, I took my sum. Right. I just did that. I just took my sums and I got those answers, right? Okay, so now we can move on to the limit part of our adventure. Okay, so what are we going to get? All right, so I could clean this up a little bit first of all. So I could maybe cancel those, right? And so I'm going to get the limit. When I say limit, I mean as n approaches infinity, right? I just want to write it. B minus a over n times a n plus, if I get rid of those, and I distribute, I'm going to get, what am I going to get when I distribute here? I'm going to get bn plus b minus an minus a all over 2. Everybody agree? Okay. Let's distribute the b minus a over n. Okay, and we're going to get, so if I distribute that all the way through, I'm going to get Let's distribute the n through first of all. So if I distribute the n through, that's going to cancel this guy, so I'm just going to get an a, right? Plus, it's going to cancel this guy and this guy, so I'm going to get a b minus a from those two. And then these guys right here, I'm going to get plus, this is over 2, plus b minus a over 2n, right? Now what? If I take my limit, what happens?
The last one's gonna go to 0.
Right? Okay, and here's where the magic happens. Now if I distribute, what am I going to get? So if I distribute this through, I'm going to get a ba minus a squared plus b minus a times b minus a is going to be b squared minus 2ab plus a squared over 2, right? If I add up, let's get a common denominator. So let's make that a 2ba minus 2a squared, and the whole thing is over 2. And let's add up like terms. So I've got a b squared. I've got a 2ba minus a 2ab, so those cancel. Everybody see that? So those guys go away. Minus a 2a squared plus an a squared is just minus an a squared, right? Everybody agree? Okay. Over 2. I'm going to write this in a little different way. I'm going to write this in the way, I'm going to write this as b squared over 2 minus a squared over 2. Okay, and I'm going to write this even a little bit differently. It's going to be a little weird. I'm going to write this as x squared over 2 evaluated from a to b. Now this is a different notation, but what this means is this expression evaluated at b minus this expression evaluated at a. Okay? And I can even put the other side of the bracket on it. That's what that means when we put a subscript and a superscript to the side of an expression like that. Okay, that's what that implies. So now let's go back and write the original problem here. The original problem was we were trying to find the area under the curve f of x equals x, right? Okay, so if f of x equaled x, how does that relate to, that function relate to that? Without any of that algebra that we just did, can you just ignore that for a second? Can you find a way to relate that expression to that?
Without the a and b?
Without the a and b. Just the x squared over 2 and the x. Yeah.
Not take the square root. Square.
Yeah, okay, you're right, but that's, okay, that's kind of,
Is that like the antiderivative?
that's an antiderivative. What do you know? Aha. Look at this. So if we said the antiderivative or the integral of x dx, the answer is x squared over 2 plus c, right? Aha. We could have even had a plus c in there, but look what happens. When I evaluate this from b to a, even if I had that plus c in there, I'm going to get b squared over 2 plus c minus a squared over 2 plus c, and so the c's are going to cancel, right? So without the constant, that's actually the antiderivative, right? Okay, that's huge. Look what we just did. We didn't actually, okay, what we did is we found an area under the curve from A to B, right? So what if I said something like this? If I attached those limits to the beginning of the antiderivative, and we call it an integral, And then the answer ends up being, we don't need the c anymore, because we're gonna actually establish a difference between the values of the antiderivative, and the constants would cancel. And so this just ends up looking like, wow, what did we just find by accident? That the antiderivative is a lot more than we thought it did. The antiderivative actually predicts what the area under the curve is going to look like. It predicts what the area function is going to look like, right? Let's change this. Well, let's do an example of this, and then I want to challenge you to think about this in a slightly different way. So what if we wanted to, for example, then, avoid all that whole limit process, and I just want you to find the area under the function, let's do square root of x on 1 to 4. How are we going to do it? Square root of x from 1 to 4. Right? No big deal. What's the antiderivative of x to the 1/2? Right? But we don't put the plus c this time. We're just going to evaluate this from 1 to 4. Right? So what's that mean? So then our answer is going to end up looking like, we'll maybe even simplify this more in a second. It's going to look like 2/3 times 4 to the 3/2 minus 2/3 times 1 to the 3/2, right? Make sense? Okay, so what's 4 to the 3/2?
2.
No.
No. 8.
8. 4 to the 1/2 is 2, cubed is 8, right? Okay, so we get 2/3 times 8 minus 1 to the 3/2 is what? 1. Okay, so that means I'm going to get what, 14/3? That's the answer.
That's the area.
That's the area under the curve, exactly. How about that? Okay, could we have done something here that would have been maybe a little bit easier? What could we have done here to simplify this a little bit? We always want to try to pull out constants if we can. Is that appropriate here? I want you to notice something. What could we have done? Jonathan, what could we have done there? Put it out in front. Because it's going to be a constant, it's going to end up being just a common factor, isn't it? You get that? So we could have written this, and that helps a little bit. So we could have written that as 2/3 times x to the 3/2 evaluated from 1 to 4. Right? Isn't that just awesome that it does that? Wow, amazing, right? Amazing. So we write that then, so we write it this way. This is, so we actually, that bumps us up to section 4.4, which is, this is the fundamental theorem of calculus. Here's what it says. Fundamental theorem of calculus says that the area under the curve, f of x dx from a to b, is equal to the antiderivative of f evaluated at b minus the antiderivative evaluated at a, which an easier way to write that is this notation I just showed you. Is that way. Okay? They mean the same thing. Right? Okay? So then, what about this? This is what's called an area function. So how does this change? How much time we got?
2 minutes.
So what if we do this? What if I did something slightly different? What if I wanted to add up the area under, let's say, x cubed from 0 to x. Okay, first of all, that looks a little confusing to have an x there and there, doesn't it? Right? It's okay to do, but a better way to write this would be to say t cubed dt, where t is what we call a dummy variable. It's just there to define the shape of the curve, right? It works either way. But what's my answer going to be? Aren't I just going to get t to the 4th over 4 evaluated from 0 to x? Okay, so the answer then would just be, at 0, that's going to be 0, isn't it? So I'm just going to get x to the 4th over 4, right? This is what we call an area function because the upper limit, it could be the lower limit or both, but the upper limit is not a constant, it's actually a variable, right? So as x changes here, think what this is doing. This curve is sweeping out area under this curve, right? Under a cubic, what would we call that, an envelope, right? The shape of the curve is going to be x cubed, but what x really represents is how far we've swept out area, where we stopped. So as x increases, the area increases. It increases at an increasing amount, doesn't it, right? It increases as this function goes, though, right? You get what I'm saying? Okay, so we'll look at that in more detail soon. That gets you a long ways, though, right there.